Okay, so right now we've only been representing our graph as something that you can connect. Either there's a connection or there's not. That is actually a very terrible graph. Because in reality, you know, you might have 0 here, you might have 1 right here, you might have 2 over here. Is that coming up on the board? Awesome. You might have 3 down here, and you might have 4. And if there's just some connections, we'll do bloop, 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 bloop. The 3? All right. Yes, that's a 0. So the question is, if we're trying to go from 0 to 4, what's the shortest path? Let me rephrase that. If we're trying to go from 0 to 4, and we'll say that these are airports, and these connections are the time it takes, which one's the shortest path?
0 to 4.
Well, what if this is, you're trying to go from South Carolina to Florida, and this was from South Carolina to Italy to Florida?
Yeah, it depends on like how long the edges are, right?
Yes.
Yeah.
So we need to add something to this graph. We can't just say they're connected. We need to add weights to the edges. Yeah, you know, this might be, okay, this marker is dead. That was fine. I'm okay with that. So this might be 55. This might be 65. This might be 500. This might be 100. And this could be 250. So what's the shortest path now?
From 0 to 1.
Yeah.
0, 1, 3, 4. Okay. How do we represent that in this? Well, now we want to put the weights in here, right?
Yeah.
That's what we want to do. But we don't want to do 0s and 1s. That's why I was saying earlier, using 0s and 1s is terrible. But we start with it in hopes that it helps you understand how graphs are set up better. So now you need, the easy way to think of it is how much time does it take to go from one place to another? So you're at 0, how much time does it take to go to 0?
0.
No, here.
1 and 1 is 0. So you actually have zeros along the diagonal. Because if you're already there, it takes 0 minutes to get there because you're already there. All right, so 0 to 1 is how many minutes? 55.
Oh.
0 to 2? 500. 0 to 3 is our edge between 0 and 3. So usually you want to find out some way to represent that as the edge doesn't exist. There are different ways to do it. An easy way is -1. If it's negative, you can't do it. Can you go from 1 to 0? Yeah, 55. Can you go from 1 to 2? Yes, 65. Can you go from 1 to 3? Oh wait, 1 to 2 actually doesn't exist, I lied. That's -1. This one's 65. And then from 1 to 4 doesn't exist. Any questions so far?
No.
All right. Someone fill out this row to me, or for me. What goes here?
500. 0. No, that's
-1.
-1.
-1.
-1. What here?
100.
100. All right. 3 to 0.
-1.
3 to 1.
65.
3 to 2.
-1.
3 to 4.
350.
250, yes.
Looks like 350.
4 to 0.
-1.
4 to 1.
-1.
4 to 2.
150.
100.
Oh, 100. Looks like 150.
You may be right, 150 almost. And then 4 to 3? 250.
250.
Okay. Now what's the shortest path? Well, first off, let's update our code so it actually represents something similar. So when you add a directed edge, you need to also add the weight. So now we need to have the weight. And initializing the graph, well, now it's initially -1 if you can't go there, otherwise it's 0. And then when you add edges, you want to add some weights to them. So let's see if we can add some weights. 10, we're going to initialize them to 10 first, and then I'm going to start messing with them a little afterwards. Because normally it's 1, 0, 1, 6, 11. So we'll say 6 to 11 is a very expensive operation. There we go. And we'll just give these some different values just to mess it up a little. All right. So we run it, it's still not going to work. Too few arguments. Oops, we're too few arguments too. Right, because we need to forward weight from here. And whoops, good. Now we're down to probably what it just says. Oh, weight has not been declared. Didn't find anything. Well, that makes sense because we're not testing the right things down here in breadth first search. Now we're trying to make sure that I is actually greater than or equal to 1. Really, it's just greater than 0. Now it found the path. Wow, now our printed graph is not pretty whatsoever. But is that the shortest path? No. No. Because that 6 to 11 is 9,000, and taking more hops would make it shorter. Okay. Let's make sure let's see what the breadth first, or the depth first one does. Oh, it didn't even find it. Let's go ahead and update it because we're not checking the right thing, just like last time. R greater than 0. All right, there we go. Oh. It found an even longer one. So neither of these are going to give us our shortest path when we're using a weighted graph. Although breadth was giving us the shortest path when there was an unweighted graph. So the question now is, how do we find the shortest path of a weighted graph?
Whichever weight is less.
Yeah. You compare the two weights, or whatever weight of the path you could take, and like add them all together.
Okay.
And then whichever one has like the lowest value is the path you would take.
Okay, so you'd add the lowest value. So you'd try the lowest one first. Okay. Oh, that's pretty good. Let me go forward. We talked about graph traversal depth and breadth. So, are you really serious? Okay. So,
Of all the times they don't add pictures.
no, it's shortest path algorithm. Also, this one's actually called Dijkstra's shortest path algorithm. Yes, the algorithms are starting to get to the point where they're being named after the people who created them.
Whoa.
By the way, are you okay, Sydney? Usually farm the top of the
I'm dying slowly.
But really though, I just coughed it off. You know, I
I
haven't
had a
been
cough
coughing,
last night.
do while you're holding it back. Okay.
yeah.
Weight on the edge. All right, so the weight of an edge, non-negative real number. Weighted graph, every edge has non-negative weight. That's what I just talked about. The source is the start of the vertex, and the weight of a path is the sum of all the weights along the edges. So the shortest path is basically find the path with the smallest weight. It's a greedy algorithm developed by Dijkstra. Yes, that's how you spell his name, with a J. Dijkstra. I think it's one of those Dutch countries. I don't remember where he's from.
There's only one Dutch country.
Well, there's Dutch, and then there's, the Scandinavian ones will do it too. Yeah, no, that's German.
Yeah.
Good try.
Oddly Germanic.
So you have a graph, it has vertices, and you have a two-dimensional array. And we're just waiting. They used infinity if there's no edge. I'm using -1. So how do we do that? Well, you read a bunch of text right here, and it doesn't make any sense, so you go to the picture instead. So let's take this example. How many nodes are on here? 5. All right. And the weight from 0 to 1 is 16. How about the weight from 1 to 0? No.
Wouldn't it be 5 plus 4?
No, there is no. It's infinity. Because there is no edge between 1 and 0. Trick question.
You wouldn't go around.
No. No, that your JC matrix is only holding the edges that exist.
Okay.
Well, I didn't ask for the path yet.
Yeah, after there is no path, nothing connects to each other.
There's only the force.
So if we're starting at 0 and we want to find out if we can get to... Oh, the way this works is you pick a starting point. So we'll pick 0, and it's going to tell you the smallest weight to whatever for all of them. So you start with 0. You have an array that holds basically the edges from 0 to everything else. So 0 to 0 is, of course, 0, 0 to 1, 16. 2 is infinity because you don't have one. 0 to 2 is 3 because there's an edge, and 0 to 4 is also 3. And then you keep a vector of weight found, or aka has visited. And you start at 0. All right, you filled it out. Which node do you think we should visit next? We're at 0. Which one should you go to next? You're trying to find the shortest path.
3.
Yeah, you should go to node 3. Why?
Oh, because it's
The weight, smallest weight.
the smallest weight.
So it's going to go to 3, mark this as true, and then you're at 3. You're going to say, okay, I've spent 2. If I try to go, where can I go from 3? Well, from 3 I can go to 1, and that costs 12. 12 plus 2 is 14, which was less than 16, which is what we had previous, so we're going to put that in there. From 3 we can go to 4. Well, 2 plus 7 is 9, but 9 is greater than 3, so we're going to keep that old 3. You see what it did there? Now that we've gone to 0, we've gone to 3, what is the next node we should go to? 4. Yeah, because it only cost, that's the next lowest in here. So if you're at 0, the next lowest that we haven't visited is 4. So let's go to 4 next. Well, we're at 4. This is going to become true. Let's see if we can guess it. If we're at 4, we have 4 cost 10 to go to 1. So it'd be 3 plus 10 is 13, which will be less than 14. So this should change to a 13. And then we're at 4. We can now go to 2. So we know 3 to get to 4 plus the 4 to get to 2 should be 7. So we should put a 7 right here. And there's no other edges coming out of 4. So that's when we're done. What would be the next node we'd visit?
2.
2, because that's 7. It's the next smallest node that we have not visited. So we go to 2, which costs 7. We'll change that to a true. So 7, if we're at 2, we can go back to 1. What's the cost? 3, but that would make the total cost 7 plus 3, which is 10. And 10 being less than 13 should replace that 13 with the 10. So there you go. True. 10. And when we're at 2, there's no other edges, so we're done so far. And then what's the last thing we check? 1. but you're at 1, which is the heaviest weight, so you're not going to change anything else. So now you know what the shortest weight or smallest weight from 0 to any other node is. All right? Okay. We're not going to do minimum spanning tree yet next. But this is basically what your lab is to button up the graph adjacency matrix into class and then do shortest path algorithm on it. There are a ton of resources on shortest path. So if you're having problems, you know, you can look up the algorithm. Don't copy the code. But there's a lot of resources on Dijkstra's shortest path.
Don't copy the
Yeah, don't copy code.